stuff we did last time, except, like I mentioned to you guys, we're going to be a little more structured about it this time. So instead of, hey, Timmy messed up the chain rule, we're going to say, what if you wanted to do step 1, 2, 3, 4, 5? And with a lot of these, you could still do Timmy messed up the chain rule. And so once we kind of navigate our way through this, I'll kind of point out the places where you need to do this and the places where you'd have an option. And really, honestly, where you have an option, you truly have an option. You can pick whatever seems to work best for you. Okay? So I encourage you to think about your decisions and choices there. So number 1 is the one we're going to start off with. And number 1 would truly be a one where you'd have absolutely have a choice. You would not have to do what I'm about to do. You could do the Timmy messed up the chain rule pattern, whatever. It's totally up to you. Let me show you the more structured way. This is called change of variable or sometimes substitution. And the way you do this is you always make your u. This is kind of like what we did. We did one of these yesterday. You always make your u your inside function. So in this case, what would you guys say is the inside of the composite? 2x minus 1. So over here, I'm just going to get things organized and say, all right, u is equal to 2x minus 1. Okay, so as we set that up, we're always going to find du. And so in this case, I think I'll insert like a little in-between step here. So the step I'm doing in red, you really don't have to do or show. I'm just going to do a derivative. So it would be du dx equals what? 2. So du dx equals 2. But what I'm going to encourage you guys to do is mentally, like when you're doing that, just mentally multiply the dx over to the other side. Like always do that. So I would encourage you to just write du equals 2 dx. To me, that would be something, you really don't have to write the thing in red, right? You can just mentally multiply it over and we're done. Is that good? Once you've done this, we're going to start trying to substitute. So I'm going to say then that 2x minus 1 is u, so my first step of substitution would maybe look like this. Antiderivative of u to the 1/2. But I got to acknowledge that the dx is still there. I can't just be like, dx, be gone. We'll just ignore you or whatever. It's still there. Let me complete my substitution real quick. And then I need to complete my substitution by getting rid of the dx and putting something in its place that is only in terms of u. So what I would do here then is divide both sides by 2, and I'd get du over 2 equals dx. So really, honestly, this is just substitution. And all we're doing is we're trying to manipulate stuff to get to a place where I can get all the x's out and only put u's in. So I could then, for my next step, write integral or the antiderivative of u to the 1/2 times du over 2. And one thing that I'm always going to do when I'm doing these, just because I have a lot of experience with this, instead of writing du over 2, I'm just going to immediately mentally pull the 1/2 out. You can see how that du over 2 is really 1/2 du. So I would probably get to here pretty quickly, 1/2 antiderivative of u to the 1/2 du. Okay, so at this point, your substitution is totally complete, and we'll be able to finish this pretty quickly. Question, Anna?
I have like 2 questions.
Sure.
How do you just get to pull the 1/2 out of the, when it's inside the antiderivative?
So it's the constant multiple rule. So if you remember, we looked at this like early on when we were doing antiderivatives of c times f of x dx, where c is just some constant. Then what you can do is you can bring it out and multiply it times the antiderivative, do whatever you got to do with the antiderivative, and then multiply the c back in at the end. So that the constant multiple can move in and out of the antiderivative symbol with no adjustment needed.
And then I don't understand what the point of like declaring what u is if it like we don't do anything to it like the whole time. Like why you had to declare 2x minus 1 as u if you just could have written 2x minus 1 to the 1/2. Like,
so yeah, so I agree with you here. Like I look at number 1, and if I were taking some quiz or test myself and I was doing one, there is no chance that I would do u substitution with this question. I'd go times 2 times 1/2, bam, bam, done.
But doesn't you never change the substitution? Couldn't you never change the substitution because it would just be what's inside?
Yeah, u is always going to be what's inside. What you're going to find, I think, here in like 2 examples, you're going to find a situation where you're like, whoa, okay, this substitution makes a lot of sense here, right? In this one, I don't think substitution makes any sense in number 1. To me, mess up the chain rule pattern will work great, and it'll be way faster.
Can we do one where like of the ones that are like only substitution work?
Totally, yeah, we definitely will do that. I just wanted to start you off with a really easy one that you could kind of confirm using the method if you wanted to. I just thought I'd start off real easy. Okay, so then the way we finish this is we find our antiderivative. So it would be 1/2 times u to the 3/2. And then, of course, divided by 3/2 is really times 2/3 when you do your power rule for antiderivatives. And then don't forget your plus c at this point. Once you've done your antiderivative, you found it, the tall skinny s is gone, the plus c is there. So a way to think about it is if the tall skinny s goes away, you better be a plus c, right? And then my final step would just be to plug back in what the u is. So the coefficient ended up being 1/3, and it would be 2x minus 1 to the 3/2 plus c. You can always check this by doing a derivative. You'd have to do a chain rule to check it, but should work out fine. Yep, this is it right here. So this essentially what this is the function that if you differentiated it, you'd get the original integrand. So we found an antiderivative. Yeah. Okay, so I want to give you guys a chance to practice that on your own. So if you would, is there a question on this one? Okay, so I'm going to show you one that's real similar. We're going to skip a little bit. If you guys go to number 4. And I want to manipulate number 4 just a little bit to kind of help get you into a good place, but then I'll turn you loose on it. What would be the one thing you'd need to do before you did any of this stuff? Bring up. Yep, flip it up. So it would be antiderivative of 3x minus 1 to the what? -4. Yep. So that goes here times dx. And this is where I'm going to turn you loose on it and see if you can use substitution. Please do use substitution. This would be another one where Timmy messed up the chain rule. Would be really easy. But I want you to practice this. The next two we're going to do, one of them, substitution will be mandatory. The other one, it'll be very, very helpful. Brendan, what did you make your u? If you wouldn't mind sharing. Okay, 3x minus 1 for your u certainly makes sense. And then Nick, obviously we've got to find the du. What did you have for du?
3dx.
3dx. Well, let's stop for a second. This, of course, is going to be the basis for all the substituting that we try to do. So we got to have this right? If we mess this part up, we're going to be in some trouble for sure. So do you guys have any questions about why either of those is what they are? All right. So then the u, being 3x minus 1, would replace it. So that would give us u to the -4th. And then any suggestions on what I could replace the dx with? Du over 3, right? So we're getting that by dividing both sides by 3. Du over 3 equals dx. That means I can replace the dx with du over 3. And I got to be honest, if I were doing this question, what I would do is this. I would go du over 3. Okay, I would just kind of combine that into one step. I mean, you're substituting when you're pulling the constant multiple out. I think that's okay to do. Okay, so from here, you find your antiderivative. So it'd be 1/3 times -1/3 u to the -3 plus c. And then you'd plug back in. You'd plug the 3x minus 1 back in where it goes. So -1/9 times 3x minus 1 to the -3rd plus c. And there's an antiderivative. Questions? So I have a question for you. We got 2 more to do like this. Would you guys like to do the one where the substitution is essential, like there's no way around it, or would you like to do the one where it's just extremely helpful next? Essential? Okay, cool. Fair enough. So let's do number, I think it's 2? Yeah, so number 2, substitution is completely essential. And I really like number 2 from the perspective of, we've talked about this a little bit, but I would tell you that antiderivatives can be very, very challenging, because if you take an integrand and you make like one little tiny, seemingly insignificant change, it's actually could be a huge change. And I think comparing 1 and 2 is a great example of this. Did you notice that number 2 is exactly like number 1, except there's an extra x? It completely changes. And so you got number 1 right there in front of you. I think you'll look at number 2 in the end and be like, whoa, okay, that x made a giant difference. Okay, so we are going to, let's approach this from this perspective. You're taking some test, you're taking some quiz, and this is number 2 on the test. Out of context, how do you know what to do? Well, you look at your integrand, and remember that pattern from last time? There's a product, but the more important part of the pattern is that one of the factors, or both perhaps, is composite. You see the composite part? Okay, so we are going to proceed, just like we have with the other ones, we're going to set u equal to the inside function. What would you say is the inside function? 2x minus 1, that's right. Okay, so far so good. And then just like before, we're going to find our du. What would you guys say our du is based on that? 2dx. Okay, awesome. So then what we would do is we'd start substituting. And here's the thing. You got to be intellectually honest about this. Things can't just disappear because you want them to disappear. They got to go somewhere, and there's got to be a good reason that they went where they went. And so we're going to start substituting. And so I'm going to have antiderivative of, well, I guess I could write u to the 1/2, right? And then I still got that dx hanging out there, and I still have that x right there. So my substitution is in process, right? I'm certainly not done with it, but it's in process. What can I replace the dx with? Du over 2. So it'd be antiderivative of x times u to the 1/2, and then times du. And just like before, I'm going to put the over 2 out front. Still doing okay? And this is the intellectually honest part. Like if you're intellectually dishonest, here's what you're going to do. Goodbye, x. Right? You're going to just like wish it away, and it's going to disappear, and you're going to be wrong, of course, right? So we can't just do that. Like I said before, all we're really doing here is we're trying to use algebra to help us take everything that's in x and turn it into something that's in terms of u. So does anybody have a suggestion? Does anybody see anything that we could use to get to the place where the x gets to go away and gets replaced by stuff with u's? What do you see, Nick?
We can use our u and then isolate our equation of u and then isolate that.
Yes, that's it. Nice job. That's really good. This can be really challenging. There have been classes in the past where I've presented a question like this, and I ask that question, and I'm greeted with like extended silence, and then more extended silence, and it takes a long time, or maybe no one figures it out. So, Nick, awesome job to see that. So we're going to do that. Let's go a little bit deeper with this. Nick suggests that we use this and solve for x. Here's why. That is the only thing on our whole paper that relates u with x. And so that's the thing we have to use. There's no other relationship that'll work. So I'll just take his suggestion. We will add 1 to both sides and then divide by 2. So u plus 1 over 2. All right, so then we can come back over here and be like, cool. Let's do some substituting. I've got this 1/2 hanging out here from before. I've got my u to the 1/2 from before. I've got my du from before. And now I'm going to replace that x with u plus 1. Got to put it in parentheses. Parentheses are super important here. And then are you guys okay if I put the over 2 again out here? So now there's 2 of them, right? It's not the same 1/2. They came from 2 different places. But I'm just going to, any constant multiples I can get out of there, I'm going to get out of there because the fewer fractions especially, smaller numbers in there, better, right? And so I'm going to continually try to pull out constant multiples. So Nick noticed something really important. You guys all okay with the substitution with all that put together? I got to be honest with you. Well, actually, I'm going to be honest with you in a second about something else. Can you guys see here how substitution is mandatory? Timmy would have been off by a factor of x. And you would have been like, can't do it. But you actually can do it by substitution. Okay, so I want to say that. So, yes, truth here is we've done a lot of work, but there is a major hole in the ground that you could fall into that we want to avoid. Okay? Let me just be straightforward with you. This was a product. What is this? Still a product, right? And you're going to find that the antiderivative of a product is very problematic. We are going to avoid it as much as possible. And we can deal with it with some Timmy messed up the chain rule stuff and some substitution, but we already did substitution and we still have a product. And that's a problem. So does anybody have a suggestion as to what we could do to make it not a product? Distribute. This is mandatory. You don't have a choice here. You have to distribute this. And so I'm going to distribute that 1/2 throughout. I can only do this now that I have substituted. So if I do this, I'm going to get 1/4 times the antiderivative. Suggestions. When I distribute, what is u to the 1/2 times u? U to the 3/2. There you go. Add your exponents there. And then, of course, 1 times u to the 1/2 is just u to the 1/2. After all that work, we are finally ready to find an antiderivative. And like I've said, this is where substitution is mandatory. So this would be, I would certainly put this on the outer reaches of challenging questions like this. This would be certainly one of the tougher ones. Okay. All right, so let's do our antiderivatives. So it'd be 1/4 parentheses, I guess it'd be u to the 5/2 times 2/5 plus u to the 3/2 times 2/3 plus c. And you could leave your answer in a number of forms. I'm going to try to make mine as clean as possible. So I'm going to multiply the 1/4 throughout there. 1/4 times 2/5 would be 2/20. So I'm getting 1/10 u to the 5/2. And then 1/4 times 2/3 would be 2/12. So that would be 1/6 u to the 3/2 plus c. And of course, your final step would be to plug what the u really is back in, right? So it'd be 1/10 times 2x minus 1 to the 5/2 plus 1/6 2x minus 1 to the 3/2 plus c. Okay. So this is your motivator. This is why you want to make sure that you're good at substitution, right? Because if you see something like this or another one coming up, you want to be able to do this. Okay. Questions, concerns, comments, anybody? Okay. So let me show you the other one here that I would put this in the category, this number 3 here. I'd put this in the category of U substitution is extremely helpful. This could certainly be done with Timmy messed up the chain rule. But I got to be honest with you and say that I don't necessarily recommend that. I think that U substitution would maybe be a better choice here. That is a matter of opinion. You feel free to disagree. Totally up to you. Okay, so check it out. Number 3, antiderivative of sine squared of 3x times cosine of 3x dx. Cool. So you look at this. Isn't it pretty obvious that this involves some composite stuff? That's kind of all over the place, right? So then when you think about, all right, we're going to do U substitution here. The U needs to be the inside function. What would you guys say is the inside function? Sine of 3x actually is an inside function, but isn't there another inside function? 3x. So this is one of those things where it's like a box within a box, and then that whole thing is within a whole other box. So instead of composition of 2, it's composition of 3. Right? So this is not f of g of x, this is f of g of h of x. 3 of them put together. So I do have some advice for you, because you could make your inside function 3x, no problem. You could also make your inside function sine of 3x. And maybe, you know what, this would probably be wise for me to write this out. Are you guys all comfortable with the idea that sine squared of 3x is really sine of 3x, quantity squared? Like as far as notational stuff? Okay. So you definitely would need to see that in order to understand this. So of all the boxes in our little analogy here, which would you guys say is the tiny box? 3x is the smallest one, right? What would you guys say is the medium-sized box? Sine of 3x, right? And what's the big box? Not cubed, something squared, right? Sine of 3x squared, technically. Okay, so here's my advice to you. I think that this makes it easiest. Because you could make your u 3x, but you could also make your u sine of 3x. I always would suggest that you use the medium-sized box. The medium-sized box for your u. So in this case, the medium-sized box would be sine of 3x. I really think that this makes this easiest. So as you pick them out and you say, hey, there's a tiny box, there's a medium box, there's a large box, it's going to come down to either tiny or medium, right? Use the medium one, I think, is probably your best bet. Okay, so based on that, what would you guys say your du is? Yeah, you actually have to use a chain rule for this, don't you? 3 cosine of 3x. Because sine of 3x is composite. To get your du, you're going to have to... Oops, sorry. I forgot my dx. There we go. Does it matter what?
If you put the 3 before or after?
It doesn't
Is it
matter.
just more helpful?
Your choice. Totally your choice on that. Okay, so like before, once you have your Your u and your du set up. Now it's time to substitute. Are you guys all okay with this? Antiderivative of u squared. Right? So we're replacing the whole sine of 3x with just the letter u. And then you still got this cosine of 3x hanging out there. We got to be honest about that and say, yeah, we don't know what to do with that yet. And then what could we replace the dx with? Over that whole thing, right? Yeah, so it'd be du over 3 cosine of 3x.
Can you also put that on the outside? Like, just do
Part of it,
u
yeah,
and then
part of
put
it
one
will,
over the rest of it on the outside?
part of it will go to the outside for sure. So here's how this works. If dx equals that, couldn't I replace dx with du over 3 cosine of 3x? Why would this be so helpful? Yeah, the cosine of 3x's, they divide out to be a 1. So cosine of 3x, cosine of 3x. And based on that substitution and subsequent cancellation of those common factors, we are now in terms of u. Did you notice the 3 still hanging out there? So I'm going to write that on the outside. So it'd be 1/3 times u squared du. And so earlier I said this is going to be a situation in which substitution is extremely helpful. Can you see why that would be? I mean, check this out. Here's your original integrand. After you've substituted, there's your new integrand. Do you see how we've made this through the substitution, which may or may not be challenging, but through the substitution, we've made the integrand and therefore the antiderivative way easier. It's going to be so much easier. Okay, so once you've done this, we're going to just kind of proceed as we have been. We're going to write 1/3 times the antiderivative, which would be 1/3 u cubed plus c. And my final step would just be to plug back in what my u is. So it'd be 1/9 sine of 3x quantity cubed plus c. Anna,
Can you show us this the other way, just to see how it would...
the Timmy messed it up? Yeah, before I do that though, are there any questions on this one? Okay, cool. So then if I was going to do the whole Timmy messed up the chain rule thing, what I would do, I would, at least in my mind, I would think about this. I'd say, all right, well, this is really sine of 3x quantity squared times all this. And then I would look at this and say, all right, here is my inside function. And I would say, what's the derivative of the inside function? And I would think to myself, I'm doing this in my head, 3 cosine 3x. And I'd say, well, is the other factor that? No, but it's really close, right? He's only off by a factor of 3. Come on, Timmy. Times 3 times 1/3. And then all of this, there we go. All of this gets folded back into the input. And the only thing that I really have to do an antiderivative of is the outer function, which is squared. So if I do an antiderivative of squared, I get 1/3 times input cubed, and I throw in my plus c, and I'm done.
Times the other 1/3.
Oh, times this 1/3 that was already out there. So 1/9. So like you're doing the bulk of this in your head. And if you're comfortable with that, for goodness sake, do it. But you'll run into ones like number 2, where all the work in your head in the world is probably just going to twist you into a mess. So I'd rather not try to do that. But this one certainly is doable. Yes, ma'am.
Since this is 3 composite functions, what happens to its mean? Because that's the derivative.
So the 3 is part of the derivative of the inside. Right? So think like
Because you got 3 cosine.
if you, so you've got, whoa, what happened there? There we go. So you've got 1/9 times sine of 3x cubed plus c. If you were going to do a derivative to check this, like the answer to your question really, Eden, is where did it come from? So the 3 times the 1/9 would be 1/3. It'd be sine of 3x quantity squared. But then you'd multiply by the derivative of the inside, so that would be cosine of 3x. But then you'd have to finally multiply by 3, the derivative of the most inside. And so then when you ask yourself, where did this 3 go? It just went right back inside where it came from, just like this did. They both get driven right back into the input. Okay. Any other questions? Okay, fantastic. So then I think we just have two more of these kind of antiderivative questions. And these, 1, 2, yeah. So these last two questions have to do with just a slight tweak to what we've been doing. The question really becomes, cool, we know how to do these antiderivatives with the Timmy messed up the chain rule thing, the substitution thing, and with all of those we got plus c, so we're finding these antiderivatives. Now the question becomes, what if it's a definite integral? What if there are limits of integration, right? Like in this case, number 1 here, it's from 0 to 1. What could we do with that? Is there a way to navigate this more efficiently? And I think there is. So again, we're going to look at how you change the variables for definite integrals. And the thing here that's written at the top, I think it's super important to realize that, like we've been doing, whenever you substitute, all of the x's need to be replaced by u's. The thing that you might forget is that the limits of integration, like in this case, the 0 and the 1, those are also in terms of x. Think of it in terms of area. Do you remember how we found, and we'll do this question here in a second. Do you remember how we found area? We said, hey, let's got this curve right here, and let's find the area from 3 to 7. What kind of numbers are the 3 and the 7? They are x's. Okay, so if the whole integral is in terms of x, we are led to assume that the 0 and the 1 are also x's. So the only real added piece here is we need to deal with those limits of integration. We'll talk about how to do that in a second. Make sense? Just go back and think about how area worked, right? It was from x equals this to x equals that. We need to convert those over to u's as well.
Do you have to use a u substitution when it's definite integral?
No.
I was just asking.
No, and I'm just being honest with you. You don't have to do it. I'm going to show you a question here in a second that's going to assess whether you know how to do that or not. But if you can find the antiderivative without doing substitution, you could actually do this without substitution. You really could. But you'll for sure be assessed to see if you know how to do it. So yeah, I'll show you that in a second. Okay, so guys, much of this is going to feel exactly like what we've just done. Your u is still going to be your inside function. We're still going to find a du, and all that stuff's going to be the same. It's just, can we deal with the limits? That's going to be the question. Okay, so for this one right here, what would you guys say the u would need to be? Yep, x squared plus 1. And what would you all say the du would need to be? 2x dx, that's right. Okay. So then with this in mind, I'm going to go back and start trying to substitute a little bit. So I am, for the moment, just going to write an integral with no limits. It'll just be antiderivative for now, and I'll deal with the limits later. So if u is equal to x squared plus 1, I think I could safely write u cubed right there. I'd still have an x, and I'd still have a dx. And then I need to see what I can do with the dx. What would you guys say I could replace the dx with? Du over 2x. That's right. We're just going to solve for dx, which gives me du over 2x equals dx. And then I can use that to substitute. And hopefully you see a lovely pattern developing. You end up with antiderivative of x times u cubed times du over 2x. Still haven't done anything with the limits yet. I'll do that in a second. What's the nice thing that happens when I substitute like that? The x's cancel, and I'll get the 1/2 out. So I'm going to write 1/2 antiderivative u cubed du. So I'm about ready to finish this, but before I do, I need to handle the limits. So I've been leaving the limits off here for the last couple of steps. Now I'm going to put them back in. So my old low limit was 0. How do you think I could find my new low limit? That's right. What's the only thing that relates u with x? It's this, u equals x squared plus 1. So I'm going to say if x is 0, u equals 0 squared plus 1. Of course, that's 1. So my new low limit is 1. What would you guys say the new high limit is? 2, yeah. So u equals 1 squared plus 1, and that's, of course, 2. So there we go. All right, so what we've done here is we have converted everything over to u's. The integrand, the differential, the limits of integration, everything is u's, and we're going to leave them in terms of u. This is an equivalent expression, and so I'm going to find my antiderivative. So it'd be 1/2 times 1/4 u to the 4th. I'm going to evaluate that from u equals 1 to u equals 2. And then using the fundamental theorem, I would get 1/8 times 2 to the 4th minus 1/8 times 1 to the 4th. And 2 to the 4th is 16. 1/8 of 16 is 2. 2 minus 1/8. That would give me 15/8. Okay, so big takeaway, can you guys see how this is exactly the same as what we've been doing, except we take the limits and we convert them over to u's? Okay, so to Anna's point earlier, do we have to do this with definite integrals? And really, honestly, the answer is you don't have to. A lot of cases it's going to make it easier, but you could certainly navigate your way through by substituting back in and leaving your limits in terms of x and all that good stuff. Or you could even do Timmy messed up the chain rule here pretty easy. That wouldn't be out of the realm either. But I do want to say you will certainly be assessed on, do you know how to do this? We'll get to that in a second. Yes?
Let's say you get the integral without using like the numbers, plugging in the x's.
Okay.
Let's say you like switch the u back to x squared plus 1.
Uh-huh.
If you were to like find that antiderivative, could you just use 0 and 1?
Yes.
Okay.
And that's kind of what we're talking about. Like, yeah, you could like plug back in the x squared plus 1. And then if you do that, your limits have to be 0 and 1 now, right?
Yeah.
So like everything has to be weird. It has to be all x's or all u's. You don't want to mix.
Okay.
If you have a mix, it's going to be an issue.
I found, like,
So can I show you like a common error here?
Yeah.
Let me show you something. So I've seen people do this. They've gotten to this point right here, and they've said, oh, like, it's just out of habit here. They'll say, I need to plug the x squared plus 1 back in, and this is where they've made a mistake. Here's why it's so bad. This is now in terms of x, and really, honestly, there's nothing wrong with that, but these are u's. Do you see why that's a problem? Like everything has to be x's or everything has to be u's. You don't want to mix.
But it could be
So you
0
would make
to
that
1.
0 to 1?
Yeah, if you wanted to go back and be like, oh, I don't like that anyways, I'd like to make it 0 to 1, you'll get the exact same answer as what we got when we stayed with u's. These are great questions. Anybody else? Okay, so then the situation, like, if all I ask you to do is find the value of a definite integral, I don't really know, and frankly, I don't really care if you use substitution or not to get there. If I want to really test whether you use substitution, I'm going to ask you a question like this, okay? So this says, which of the following is equivalent to that definite integral? You've got 4 options. You can clearly see that someone's tried to convert these over to u's. Your job is to decide which one of them was correctly converted over to all u's. Does that make sense? So this is how this skill would probably be assessed. Unless I specify you got to use substitution, then I got to look through all your steps too. So give it a shot. Yeah.
On the last one.
Yep.
What would the final answer have been? Like, was it not asking you to solve the definite integral?
It was asking you to fully evaluate it. Yeah. So I got 15/8.
okay.
So if you did it with x's, you would have gotten
Just plug it back in.
yeah 1/8 times x squared plus 1. Evaluate it from 0 to 1.
Mhm.
So you'd get 1/8. 1 squared is 1 plus 1 is 2. Oh, it's to the 4th, right? Or what was the x part?
Yeah, it's
To the 4th. So you get 1 plus 1 is 2, 2 to the 4th, minus 1/8. Then you get 0 plus 1 to the 4th. You can see that that's going to end up being the exact same value
Yeah.
as what we had. Looks
okay,
a
I was
little
just
different at the
asking,
start.
you didn't
But
like circle it. Left it. It's-
sure. Yeah, if you evaluate it all the way, you'll get the same thing. Yeah. Okay, so yeah, multiple choice here. We're just looking for A, B, C, D. you can see that there's a lot of similarities and there are some important differences, right? I hope you can see how someone could easily accidentally pick the wrong answer, right? If all they did was look at one particular thing, I can totally see why they'd be like, oh man, that's right, but they forgot something, right? That's wrong. Looking for an equivalent expression to that original definite integral. Of course, you have a 25% chance of just guessing this right, so let's make sure we understand why. We'll move to the end and feel free to ask questions and be thinking through your steps and such. And how it is,
How old is your daughter?
she's doing like refractive therapy with foam-rise, so she wears a patch at night for a couple of hours to like help the other eye get stronger. And you can order all these different types of patches. You use one every day, and she likes the camo. There's purple camo, there's green camo, there's gray and black camo, and something else. So whenever we order them, I let her pick. And she's like,
What was that for? Is like just one of her eyes not as
one of her eyes is quite a bit weaker than the other, and so she wears glasses, but then we cover up the strong eye so that the weak eye is forced. Because otherwise, the weak eye will just be like, yeah, I'll let you do it, lefty. And righty's like, and so it will affect her vision in the future if we didn't do that. So she's into it now. At first she didn't, she hated it, but now she's all good. Say again?
I had a lazy eye when I was
Oh, and that's how it presents. That's what it looks like, because that one eye is like really just kind of giving up, and it's like, yeah, you don't need me. And so, yeah. That's how we first knew that her vision wasn't very good, as we could see one eye just sort of like doing its own thing and kind of like, that's not good. And then, but we got it figured out. So it's amazing what eye doctors can do, even with little tiny kids. Okay, what do you guys think? ABCD. C? C? Have we all arrived at C? Okay. C is incorrect. I like it. So let's see here. I like the limits, right? So if you change your limits over to U, 0 and 7 makes sense. So I think that eliminates A and B, because those limits have to be U's, not X's, and the 1 and the 2 are X's. And so the 1/3 really would be the differentiator here. Why do you guys think that the 1/3 should be out there in the front?
because Timmy was off by a factor.
Yeah, Timmy messed up by a factor of 3. Or when you did your substitution, you had that 1/3 to bring out. I mean, however you want to look at it. I think C does make sense. Okay, fantastic. We good? Okay, so the final little topic here, we're going to go back to a little bit of graphing. And this is going to take you back to some old pre-calculus-y kind of stuff. Even and odd functions, you remember this? Ooh. I think graphically this will probably make a lot of sense to you guys. So let's go over some basics with evens and odds. Even functions are symmetric with respect to the what? The y-axis is correct. So a classic example of that would be y equals negative x squared plus 4. What kind of a graph is that? It's parabola. Opening which way? Down shifted where? Up 4. Yep. So if we were to try to sketch this out, it would look about like this. I think your intercepts would be here and here. And here goes nothing, parabola. Now that I'm very happy with. Yeah, I'm going to give it one more try. Okay, we're just going to go with that. Okay, so there's your parabola. And you can obviously see the symmetry, right? About the y-axis, the left half and the right half are the same. So if I told you that the definite integral from -1 to 1, in other words, from here to here, if I told you that that definite integral was 22/3, which I'm pretty sure it is. It's been a while since I did that one, but hopefully I didn't make many errors there. If I told you that was 22/3, but then I asked you this question, what is the definite integral from 0 to 1? Wouldn't you say 11/3? Shouldn't it be exactly half because of symmetry? And I would agree with you. This would be 11/3. Okay? So I think you can use symmetry to help you hopefully make a quick and good judgment on what an area or a definite integral of that would be simply by using the symmetry of the situation. So a graph would be helpful here, or a calculator. The general principle is if f is even, then the definite integral from negative a to a is the exact same thing as twice the integral from 0 to a, or twice the integral from negative a to 0. So there's a number of ways this could be arranged, and if you think about a graph, I think that'd be helpful. So my advice to you would be, if you see some question that's like, hey, such and such is even, such and such is odd, which we'll look at in a second, I would sketch out a rough graph of what it could look like. And I think that would really help you understand the question you're being asked. Go ahead.
So if you wanted to solve this without a graph,
Mhm.
would you need to know like on some of the ones we do on WebDesign, you have to like know what dx is to like, do you know what I'm talking about? Where
Know what
it
dx.
was like, it would tell you what dx was because it was like multiplying the function.
I don't remember.
But if you wanted to solve this without a graph, would you just say like
We know what f of x is, right?
one of f of x and then just like solve it?
Yeah. Yeah, if you didn't have a graph or you didn't recognize that this is an even function, I would just go antiderivative, evaluator from 0 to 1, plug in the 1, plug in the 0, subtract, game over.
Okay.
Yeah.
And then I was saying like on the WebDesign some of them before it would be like f of x is 2, and then there would be a question that was like f of x plus 2 in parentheses like times dx. And so with the
Oh.
here's was-
Can we talk about that in a second?
Yeah.
Yeah, I'll show you a quick way to think about that. So let's talk real quick about odds. Odd functions are not symmetric with respect to the y-axis, but with respect to the origin. Yes. If a function was symmetric with respect to the x-axis, it wouldn't actually be a function. It would fail the vertical line test. Vertical line hit more than one point. So origin is your symmetry here for odd functions. An example is sine. So I'm going to try to sketch out sine as best I can. And something like that, roughly. That makes sense? I'd try to hit pi roughly, 3.14. Okay. So if I told you, and this is true, that the integral from 0 to pi, so like right there, if I told you that that integral was 2, but then later on I asked you what is the integral from, say, negative pi to pi, what would you say? So the integral from 0 to pi, which is that purple region, the integral from negative pi to pi would be 0, wouldn't it? Because if we really do have symmetry, wouldn't this integral accumulate to be negative 2? And then when it's added to the 2 that we already know about, you would get 0. So a general principle is if g is odd, then the integral from negative a to a of g would be 0. And again, a graph would be helpful here, understanding like which part would be positive, which part would be negative, so on. So Anna, can I show you this real quick? I have exactly 1 minute, and I think, Anna, I can do this.
Yeah.
So if you have, sometimes visually this is kind of hard to see. So you have the integral from like, I don't know, 1 to 5 of f of x plus 2 dx. Is this about what you were talking about?
Yeah, and like at the top it would say like f of x is equal to.
The integral from 1 to 5 of f of x is equal to something?
Yeah,
Right, okay.
and then sometimes it would tell you like dx is like 2 or something. Or you
I don't think it would ever tell you that dx is 2.
like I could
Let me, yeah, you can if you want, but let me show you how you would be the best way to handle this. You remember how the integral of a sum is equal to the sum of individual integrals? I would split this up. So I would write this as the integral from 1 to 5 of f of x dx plus the integral from 1 to 5 of 2 dx. Because if you've got information about this, well, then you can use that information right here, right? And then this is actually pretty simple to do, right? You'd say the antiderivative of 2 is just 2x, and then evaluate it from 1 to 5. Plug in the 5, plug in the 1, done.
Yeah, that makes sense. I think what I was talking about was like I think it didn't say what like dx.
You guys are all good to go. Have a good day. Keep going.
It didn't say what dx necessarily was, but it would say like integral of like 1 to 5 of like f of x is
Yeah.
equal to.
Yeah, it might say this. Like this might be at the top of the page. Like it
No,
might.
There was like one. It was said like f of x. It was like f of x dx is equal to this. It's like you could have found what.
Wow, if you could look that up, I'm sure we could figure it out.
I don't know.
Have a great day. Just make sure you bring stuff to work with tomorrow so that when we're doing our review and practice and stuff, you'll have some good material. I might bring up a few things for you. Okay, that's fine. Yeah, just